A very good morning everybody. Welcome to the class on smart materials and intelligent system design. So, this is the final round of intelligent system design. In this section, we will actually talk about MEMS. Now, in the previous lecture, just to recapitulate, we have talked about various electrode configurations. We have talked about the design issues that comes when we do the electrode design, and also the effect of pyroelectricity, and we just introduced the intelligent MEMS devices which can be developed based on the smart materials. So, that brings us to the context of this lecture, where we will focus more on this particular aspect, which is called micro electromechanical system or MEMS. So, here we will first start with a little bit of a case history of sensor applications, particularly in the automotive industry, and then we will talk about this MEMS in motion, MEMS developed accelerometers. All these things are actually based on smart materials in most of the cases. Then MEMS applications, then how do you actually develop the basic material for MEMS, that is the silicon based system, and then how do you develop the MEMS system out of it, and finally, the processing techniques. So, let us start with the evolution of sensors in the automotive industry. Now, because MEMS has a very interesting relationship with it. As it happened that till 1960, as you can see in some of these classic automobiles, radio was the only electronic systems, and the engine system was controlled entirely mechanically. But then these conventional mechanically actuated system, mechanically actuated ignition and fuel system, they were not good enough to control the combustion process. So, as a result, there are a lot of emission related issues. So, you would be if you go back to history, you would see that by that time most of the cities of Europe got heavily polluted by the emissions from the automobiles. So, then there came the strict rules in terms of controlling the combustion process. Now, how do you control these combustion process and the exhaust emissions in automobiles? Well, that when people started thinking, the concept of electronic ignition system came into picture. We have seen one of the most sophisticated electronic systems today with in the last class on piezoelectric injection systems. But other than that, you would also need crankshaft position sensors, camshaft position sensors, these are all for controlling the combustion process, airflow rate sensor, gas sensor at the exhaust, throttle position sensor, and above all microcontroller to control the ignition. So, development of all these things actually brought us what is today's car that we see in today's market. But then the development never stops. In fact, after that 1970s thrust of developing these basic sensors for controlling the combustion and the emission process, the next goal became the anti-lock braking device, because many a times while actually applying the brake, there is this sliding problem which used to create lot of accidents. So, the sensing of the locking of the wheels which actually creates this problem and accordingly modulate the hydraulic pressure, that actually brought forth the development of anti-lock braking device. Once that is done, then people thought, okay, we can now control the braking force by modulating the hydraulic pressure. How about controlling the acceleration also, because that can help when I am actually accelerating and then the vehicle is slipping. So, then came the traction control system, which sends slippage during acceleration and modulate the power to prevent the slipping. Then there are much more advanced systems that have been developed, like vehicle dynamics control and millimeter wave radar technology with GPS based traffic updating. So, all these things, as you can see, that starting from 1970s as the development happened, we are now well crossed this domain, even where this vehicle optimization is integrated processing, software development, all these things have taken place, and automobile is more of a computer and electronic system now than of a mechanical system. Now, one of the fantastic final development in this direction, which has also a very interesting similarity with our development of smart material, is the development of intelligent car. You must have seen these Google's Waymo car, also there is this Tesla's car. There are many such cars which we now call today self driving cars. Now, what are the important technologies that is there in self driving cars? Well, they have radar, they have the laser light, they have GPS, odometry and computer vision. So, whatever input that goes into from the driver's brain, all these things are being collected through this kind of sensors. But then finally, you have to also simulate the brain. So, then there comes the artificial intelligence also integrated into the system. Now, there are several stages of this autonomous driving. So, but these actually landmarks our journey from automated system to autonomous system. Automated systems are systems where sensors are there to help mankind, but then when I come to autonomous system, then actually the system becomes intelligent enough so that it takes its own decision. The level 1 of the autonomous vehicle drive is called hands on, where the autonomous system and the driver works together, for example, adaptive cruise control. So, these two both of them are helping each other, but in hands off system, that is the level 2, autonomous system takes care of all the important things like braking, acceleration, steering. However, a human contact is necessary for any emergency takeover. Level 3 is called eyes off, where the driver can safely take his eye off and the vehicle will drive on its own, except it may call driver's attention for some specific decisions. And level 4, which is the highest stage, is called minds off. No driver attention is ever required at this stage. So, that is something that is the ultimate goal of development in terms of automobiles, and today's topic MEMS play a very important role in this direction. Now, why do we go for these MEMS systems, which is micro scaled electromechanical system? Well, the advantage of such system over any macro scale system is that it has low power consumption, it has high sensitivity, easy to integrate and communicate to communicate with it. It has low noise and it has a high machine precision, and of course, because the development of these MEMS has been paralleled with the development of ICs, chips, etc. So, in terms of mass fabrication, the cost actually have come down. It is it has decreased the cost enormously. In fact, if you look at the market of accelerometers, you would see that how much it has been affected by the development of MEMS. While the MEMS based accelerometer they are very cheap, something like in terms of dollars only $2 to $3 maybe, and their counterpart, the traditional accelerometers, are 100 times more expensive than them. So, the integration of this IC technology have actually made this advancement and reduced the cost of the MEMS. Now, the most common application of MEMS is in terms of accelerometers. Accelerometers are devices where it actually measures the acceleration based on certain changes in the system. If it is based on capacitance, it is capacitive based sensing. It may be based on piezoresistivity. It may be based on piezoelectricity, that is what is our PZT or type of materials are used, or on optical interferometry or thermal expansion. First, these micro machined accelerometers or MEMS based accelerometer is developed at Stanford in 1979. So, you can imagine that the MEMS endeavor is here for quite some time, and yet the development is taking today it is many advancements are happening because of the advancements in the material science also. So, gyroscopes also is the second one after accelerometers, and then the digital micro mirrors. There are many such products, there are MEMS in other domains also we will see. Now, if you look at the MEMS based accelerometer first, and if you look at the fact sheet, let us say if it is based on capacitance based system, then what is this capacitor? You need a parallel plate capacitor, right. A piezoelectric material is also a parallel plate capacitor. You can also develop various other types of parallel plate capacitors. Now, in a parallel plate capacitor, the capacitance is defined in terms of that absolute permittivity epsilon 0, relative permittivity, and the plate common surface and the plate separation distance. Okay. So, that is the relationship of the capacitance in the system. So, that means this capacitance will vary. If I vary all three of the parameters, epsilon 0 is the absolute permittivity of free space, that of course, you cannot control, but if you control the distance between the plates d, you can change the capacitance. If you control the shaded area of the plate A, you can do that. If you control the dielectric constant, you can do it. Now, in many cases we try to use any one of these strategies, and by attaching such a system with some kind of a base motion, because if there is a base motion, then either there will be relative displacement between the two, okay, they will be coming closer or away, or you can also design a motion in which they will actually shear away from each other in the sense like this, one away from the other. So, that way the capacitance will change, and change of capacitance can be interpreted in terms of change of voltage. So, this is one of the such devices where there are many capacitors, as you can see in this system, and there is base at the two edge with spring attached with it. So, base is basically passing the motion to the MEMS system, and the MEMS system has many such capacitors inside. Each one of the capacitance is related to the displacement or motion x by this simple relationship. You can work it out, and so this change, the integrated effect of this change gets reflected in terms of a significant change in voltage of the system. Now, MEMS based actuators are abundant in various applications, like say automotive sector, other than all other things that I have talked about, the throttle sensors, the camshaft and crankshaft position sensors, etc. We also need actuators for airbag system, which is MEMS based, automatic door locking, active suspension. These are all actuators that are developed based on MEMS based system. Consumer sector, you have computer peripheral devices, mouse, etc., which are MEMS based, subwoofers and sports training devices. There is one very nice example of sports training devices I will talk about. Now, MEMS based systems in general industrial applications are there for condition and health monitoring, very important, where you actually the MEMS devices give us ideas about the identification of damage, detection of damage, extent of damage, damage prognosis, etc., and then detection of earthquake, shock and tilt detection. These are for general industrial applications. There are some military specific applications like explosive detections, high precision accelerometer and navigation systems. So, in all we can see that MEMS have a very important role in various applications. This is the one that I have told you that MEMS has an application in exercise control, where you can see that the size you can compare it right with this 10 cent size. So, it is quite small, and this device what it is a full fledged device. It has a sensor, it has processor and everything. It actually senses the level of stresses that is applied on the limb of a person during exercise, and the microprocessor controls the whole thing, and it gives a visual warning system that indicates that whether there is over exercise or not. Not only that, if there are continuous health monitoring and compliance control system that is attached with it, that can control the grip of the cast around the limb, that can actually also give information to the physician that about the level of exercises, etc. Now, MEMS can also be used in terms of motion sensing like accelerometers based system. So, here there is an example, as you can see that in a micro scale you can develop so many systems, and this is you can see that how each one of them can be nicely controlled and they can be synchronized, and through that you can control so many things, optical mirrors and various other types of devices including accelerometers, etc. So, MEMS has, you can see it in various forms, this system has been developed in order to create such oscillations. That is one of the applications of the whole system of MEMS system. This concept can be used also in terms of the control of an optical mirror, okay, because the optical mirrors many times in space applications, particularly for space telescopes, they are used to actually compensate the delays from various telescopes. So, if you have many such motion control systems, as you can see each one of them at the back side, then individually you can control the focusing of the system and you can actuate them, each one of them with the help of PGT actuator. If you remember that buzzer experiment, this is, you may say, a kind of many integrated buzzers together. So, thus each one of them you can actually actively control the optical aperture of the system. The issues related to MEMS development, we generally put it in a hierarchy in 3 stages. The first stage of MEMS development is related to system level development, okay, where we have to develop systems for signal processing, for networking, for packaging, design, simulation of the system. Then below that level we have the micro engineering issues. For example, how would you do the layering, micro mechanism, micro electronics, photonics, micro molding, all these issues come. And even below that we have the materials there. In that core material you may have smart materials including them. So, the foundation materials, if I start from these towards this direction, the foundation materials for MEMS, there are 3 groups. From inorganic group you can have silica, you can have silicon, you can have quartz, glass, gallium arsenide, or even the one which is mostly used today is called PDMS, polydimethyl siloxane. Metallic wise, you have options like gold, aluminum, platinum, palladium, and from the organic sides other than PDMS you have polyamides and PMMS, polymethyl methacrylates. So, there are quite a few of them, but the one which is our first choice is generally always the silica and the silicon. Now, why is it that silicon first and the best choice for us? It is because it has excellent mechanical property. It has 3 times the Young's modulus of steel, about 700 GPa, but it is as light as aluminum because its density is only 2500 kg per meter cube. So, it is an excellent material at a smaller scale. It is mechanically stable and can be easily developed by using microfabrication technology. We will talk about, we will just touch this microfabrication technology in a short while. For signal transductions, you can actually make p or n type semiconductors that can be readily integrated with a silicon substrate. So, you can develop various semiconductors also. In fact, the semiconductor industry helped the growth of silicon. Melting point is around 1400 degree centigrade. So, it is thermally quite stable for most of the engineering applications. Not only that, it has very low thermal expansion coefficient, 10 times lesser than aluminum. Now, at a smaller scale, the way it helps is that if there is a thermal expansion in the system and the other parts of the system would not be expanding, then there is a thermal stress that will generate in the system. So, that is what the chance of such generation is much less in silicon. It has no mechanical hysteresis and it is very flat for coating. So, all good reasons for silicon to be used as the most important MEMS device. Now, if you look at the crystal structure of silicon, it is basically FCC, but this FCC has generally how many atoms this FCC structure will be having. Okay. You will be having each one of them at the corners 1, 2, 3, 4, 5, 6, 7, 8. So, 8 of them, and also each one of them at the face center. So, 6 of them. So, 14 atoms. However, silicon will have 4 additional atoms to actually accommodate within this unit cell. So, it has 18 atoms. So, that makes it anisotropic in nature, and in some direction the density of atom will be less, in some direction it will be more. In fact, 100 plane it is the weakest one, and 111 plane is the strongest one. To know about these 100s, 111, you have to go through my courses of nature and properties of materials. I would not discuss these things here, but in a unit cell, if you have 8 of these atoms at the corners, what it would mean is that each one is supported by 8 such similar systems. So, that means that will be for one cell it will be equivalent to only 1 atom, and similarly for those 6 which is shared by other 2 cells, it will count will be about 3. So, 3 plus 1 will be 4, and it has 4 extra. So, each cell will have about 8 atoms in its cell. So, that is what is the crystal structure of silicon. Now, that gives the properties that we can see. For example, you can see that what is the yield stress, you can see the modulus of elasticity, and you can compare every time with this mild steel, which you know very well, in order to get some idea density versus density. Okay. You can also compare conductivity versus conductivity, a thermal expansion coefficient versus thermal expansion coefficient, and temperature stability wise. Okay. So, you would see that with all these materials, silicon is no doubt at the top of the table. Now, how do I develop pure silicon crystal? There are 2 processes. One is called the Czochralski's crystal growth process, in which what we have is the raw silica and then a silicon carbide. Then we heat it up, and we actually with the help of a seed we develop silicon, and that silicon crystal grows. We have to continuously rotate it and also move it, so that that silicon gradually goes, and we have to also take out the silicon oxide and carbon monoxide gases. The pooling rate is very critical. Okay, so that the uniformly you get a big crystal out of the system. There is another way which is more industrial way of doing, is called floating zone crystal growth process. It is also used in terphenol discs, magnetostrictive materials, similar floating zone techniques. Now, what we do in a floating zone, we will have 10. So, now what we have in the floating zone crystal growth process is that we have basically in this system a high purity polycrystalline rod and a monocrystalline seed crystal. That monocrystalline seed crystal actually goes from bottom towards the top. Okay. And what happens is that the polycrystalline part of it, that is actually by using radio frequencies, it is partially melted, and we are pulling this monocrystalline one. So, that the single crystal structure is continuously getting formed till you take the whole thing up. So, that is the float zone crystal growth process. This is very much industrially applied. The other process is that you make a vapor and let it pass through a substrate, and in a such that an epitaxial layer grows on the substrate, okay, with the same crystallographic orientation, and the substrate actually acts just like a seed. Okay. In this case, instead of the seed moving, here the substrate is fixed, and the gas that you are passing, that is actually the vapor phase. that is depositing, it is kind of like a similar to your carbon vapor, this chemical vapor deposition process, etc. So, similar to that, here SiCl4 gas, for example, with a carrier gas that will create silicon. This silicon will get deposited and HCl gas will come out from the vent. Now, while this is happening, this reaction also has the opposite side, that is SiCl4 with silicon can create SiCl2 gas, but we have to, by suitably controlling the reaction constant, we have to actually stress more on this growth happening, that is more silica should be deposited on the system. This is what is called vapor phase epitaxy method for development of silicon. Let us say we have silicon now in our hand, that is the most fundamental material that you need for the MEMS development. Now, what do? We have to develop a micromechanical system out of it. So, there are 3-4 common process. One is called bulk micromachining. In this process, we actually remove materials from the bulk substrate. So, from the block of silicon by wet etchings, by chemical reactions, or by dry etching where we use corrosive gases, or we use wafer bonding. In the case of wafer bonding, it is very much similar like laminated composites. We actually develop in this case thin wafers and then we align these wafers and develop the stacked structure, just like we have done, if you remember, for the stacked piezo actuators and things like that. So, we stack one after the other in order to form such a system. We also carry out surface micromachining instead of bulk micromachining, where the entire volume is also taken care of, only surface micromachining by the thin film fabrication process. So, this is one such process, as you can see, it is called a tape casting method. So, what you do here is that you start with a ceramic powder, solvent and deflocculant. This mixing you ball mill it for 24 hours. Along with that, now you add plasticizer, binder, cyclohexanes and you ball mill it again for another 24 hours until you get this slurry 2, that is the green slurry. Then you tape cast it, you cast it basically, as you can see that you are actually tape casting the system here and de-air it. You are going to get the tape cast sheet and you can carry out the lamination at 0 or 90 degree and you heat it up, organic removal process will start, sinter it further, you are going to get multi-layered tape cast system. So, that is the way it is done in this particular case. This is one way of MEMS fabrication. The other way is that we actually sputter. So, when you say sputter, we actually mean that we deposit thin films of a material onto a surface. So, for example, first create a gaseous plasma of the material that you want to deposit and then accelerate the ions from this plasma into some source material or the target. The source material is eroded by the arriving ions via energy transfer and is ejected in the form of neutral particles, either individual atoms, cluster of atoms or molecules. And as these neutral particles are ejected, they will travel in a straight line unless they come into contact with something. Now, if a substrate such as silicon wafer is placed on the path, these ejected particles will be coated by a thin film of the source material. So, you can either directly sputter or you first make a ionized gas and then that gas will hit the source and that source will generate the neutral particles so called, and that is going to get deposited on the silicon system substrate. So, you can get a final product by using any one of these methods, bulk micromachining or surface micromachining or wet etching, dry etching, you can get this kind of a system. As you can see that this is a cantilever beam here and this can be typically a probe of atomic force microscope and you can see that it has various layers in it if you cut it, and that various layers can be something like gold chromium deposition, silica, gold chromium and PZT, then the platinum titanium silica, etc. So, you can make a functionally graded structure, you can make a smart structure all in micron scale. You can see the length is 125 micron, width is 50, depth is only 3.35 micron. It is fascinating, this kind of development using smart materials. The processing techniques can be polymer processing techniques. One of the important polymer processing technique is called photopolymerization. So, you have there in electrochemical polymerization also, or vacuum polymerization. This is simulated by the electron bombardment on the system or initiated by ultraviolet irradiation or microwave assisted polymerization. Now, photopolymerization particularly, what we do here is that there is a photo initiation that first happens, and as these radicals are formed, they first work on the monomers, then that monomer gets a dimer, and further these things start to happen until you get this termination in terms of a polymer. So, this is used for structural polymers. Okay. Similarly, one can use it for sacrificial polymers, but sacrificial polymers, structural polymers are the building blocks, but sacrificial polymers are only needed temporarily until you build up the structure. So, then you have to dissolve it within this kind of a caustic soda solution, so that the sacrificial polymer goes away and it is the structural polymers which remains in the system. So, that you generally get a 3D structure out of it. Now, you can use various such polymeric system to develop MEMS. PVDF for example, one of them based on piezoelectricity, polyphenol based on conductivity, fluorosilicon based on electrosticktivity, silicone, polyurethane, all three are based on electrosticktivity and generally used in actuators, whereas the first two are generally used for MEMS based sensor systems as well as in some cases for MEMS based accelerometer systems. So, this is where we will put an end. In the next lecture, we will learn about energy harvesting. We will say what is energy harvesting, applications, piezoelectric energy harvester, energy conversion and a basic concept of such a system. So, that is what we will do in the next class. Thank you.